In this example, we're going to try to solve the system dy dx is equal to x plus y plus 3, and that whole thing is being squared. So to do this, we're going to recognize that this looks like it might be a perfect candidate for the right kind of substitution, as it is a nonlinear first-order differential equation in its current form. So let's see if we can make a substitution that will allow us to transform it into something that we can utilize and simplify. So I noticed that everything over here is screaming that that might be a really good substitution right here. If you're familiar with U subs in like a Calc 1 sort of situation, this fits naturally with that idea. All right, so I'm going to let v equal this quantity. And so if I do that, then it means that v is equal to x plus y plus 3. If I solve this for v, then, or for y, I would get that v, and I'm subtracting these two terms over, minus x minus 3. And then noticing here that for substituting dy dx, if I differentiate these two sides, I get that dy dx is equal to dv dx minus 1. And the derivative of a constant with respect to x is 0. So that allows me to rewrite this then with this equivalent form, which is very handy. So I have rewriting this equation with this substitution. I have dv dx minus 1 is equal to v squared, since v is the linear part there, the x plus y plus 3. Adding 1 to both sides, dv dx is equal to 1 plus v squared. And now this is really nice because now this is in a form that is separable. And so we can divide both sides by the 1 plus v squared, and we get dv over 1 plus v squared is equal to dx. Now, if you're familiar with your antiderivatives, this integral here of dv over 1 plus v squared should be screaming out to you that that's just the inverse tangent of the function that we are integrating with respect to. So integrating both sides here, and the integral of dx is just the x value. Okay, so this then is a simple integral. Integral of dv plus v squared. This is the derivative of function, so its antiderivative is straightforward. This is going to be tangent inverse of v. That's the left-hand side, is equal to x plus some constant. And we have essentially solved the differential equation for v, but our original one was in terms of y. So all we have to do now is substitute back in for what v was equal to, and then see if we can solve for y explicitly in terms of the function of x. So to do that, remember this was our value of our v, and so it might be advantageous to take the tangent of both sides immediately, and that will give us v by itself is equal to tangent of x plus a constant. And now the tangent inverse and tangent are, of course, inverses of each other, so they just produce the argument of the tangent inverse. And then this is x plus y plus 3, replacing v with tangent of x plus c. And that looks like if I just subtract over these two terms again, then I get y of x going to equal minus x plus 3 plus tangent of x plus the constant. And so that constant will be chosen based on the conditions of the initial value for the problem. Okay, so there is our substitution then, and our solution for this particular differential equation. I hope that was helpful, and I'll see you in the next video.